Welcome, aspiring pilots and aviation enthusiasts. I'm your host, and today we're jumping right into a comprehensive pre-flight briefing on weather theory. Specifically, we'll be focusing on fronts and icing. As any experienced flight instructor will tell you, understanding the dynamic, invisible forces shaping the sky is absolutely just as critical as knowing your flight controls. This explainer is designed to elevate your knowledge from, just reading a textbook to truly visualizing the atmosphere around you. That way, you can fly with supreme safety and confidence.
Okay, let's dive right into our flight plan for today. We're going macro to micro here. We'll start with the foundation, air masses. Then we'll move into fronts, which is where those masses collide. We'll decode warm and cold fronts, tackle stationary and occluded fronts, and finally, we'll explore a pilot's silent enemy, aircraft icing. We're going to cover everything you need to know. Section 1, the foundation, air masses. Before we can even begin to understand fronts, we have to understand what actually creates them. An air mass is exactly what it sounds like. It's a massive body of air that stays in one place long enough to take on the exact heat and moisture levels of its source region. Now, what's really interesting about this is that these invisible giants don't just stay put forever. Eventually, they move out. And when they do, they drag their native temperature and moisture profiles right along with them across the map, fundamentally altering the weather wherever they go. To predict what kind of weather an air mass is going to bring, we classify them strictly by their source. That source determines whether they're polar or tropical, maritime or continental. There are four main ones you absolutely need to memorize. First up, Continental Polar, abbreviated as little c, capital P. This comes from over cold land, making it cold, dry, and stable. Next is Maritime Polar, little m, capital P, originating over cold oceans, meaning it's cold, moist, and stable. Then we have the warmer masses. Continental Tropical is warm, dry, and unstable. And finally, Maritime Tropical, welling up from warm oceans, is warm, moist, and very unstable. So what happens when an air mass leaves home and starts moving over new terrain? Well, it changes. If an air mass passes over a surface that's warmer than itself, the air at the very bottom heats up and rises. This creates convective currents, which results in instability. But generally, it actually offers good visibility for flying. Conversely, if an air mass passes over a colder surface, the bottom cools down. You don't get those convective currents to mix things up. This results in very stable air, but a quick word of warning here. This often means poor visibility for your flight. Section 2, fronts, where air masses collide. When these massive bodies of air inevitably bump into each other, they don't exactly mix politely. They form a very stark boundary layer called a front. You'll want to memorize the specific symbols and colors used on your surface analysis charts. Red semicircles signify a warm front, while blue triangles denote a cold front. Stationary and occluded fronts combine those symbols. As pilot in command, you need to know that crossing any of these boundaries practically guarantees a shift in conditions. You're going to experience a change in temperature, a shift in wind direction and speed, a change in barometric pressure, and a shift in the dew point. Section 3, decoding warm and cold fronts.
We're zooming in now on the two most common types of fronts. Remember, fronts are always named according to the temperature of the advancing air. So when warm air moves in to displace cold air at a somewhat sluggish 10 to 25 miles per hour, you get a warm front. Think about the mechanics at play here. Because the advancing warm air is less dense, it can't just forcefully shove the heavier cold air out of the way. Instead, its advancing slope gracefully slides right over the top of the retreating cooler air. As this warm, high-humidity air gets lifted higher into the atmosphere, its temperature drops, condensation occurs, and a massive, broad area of clouds and precipitation forms well ahead of the actual surface boundary. So what does all of this actually mean when you're up in the air? Let's systematically break down what you'll experience. Prior to the front's passage, you'll be flying under stratiform or stratiform clouds. You'll likely be working hard on your instruments due to poor visibility, and navigating light to moderate precipitation like rain, drizzle, or sleet. During the actual passage, visibility remains pretty poor, with steady drizzle and falling pressure. But once the front passes, you're enveloped in that new warm air mass. Temperatures rise steadily, the pressure stabilizes with a slight rise then a fall, and visibility becomes fair, though you might still be dealing with some lingering haze. So that's the warm front. But let me ask you, what happens when the advancing air is cold, incredibly dense, and moving fast? Well, this is the very definition of a cold front. Unlike their slower, warmer counterparts, cold fronts are aggressive. They sweep across the terrain, displacing warm air at speeds from 25 up to 60 miles per hour. And this brilliantly illustrates exactly how they operate. Think of a cold front as a giant atmospheric snowplow. Because cold air is so dense, it stays stubbornly close to the ground, sliding right under the warmer air and violently pushing it upward. This rapidly ascending warm air causes its temperature to decrease suddenly, violently squeezing out the moisture to create towering cumulonimbus clouds stretching all the way from northeast to southwest.
The weather changes associated with a cold front are intense, concentrated, and frankly unforgiving. If we break down the conditions prior to passage, you'll see towering cumulus clouds and rapid rain shower development. During the passage itself, it's incredibly rough. You should expect heavy rain showers, lightning, hail, gusty variable winds, and extremely poor visibility. But notice what happens after it passes. Once that cold air fully moves in, you get rapid cooling, the dew point drops significantly, the pressure steadily rises, and visibility quickly turns good as the skies clear out into cumulus clouds.
However, as an aspiring pilot, you've got to know that not all cold fronts are identical. A fast-moving cold front is pushed along by intense high pressure located well behind it. Surface friction causes the front slope to steepen dramatically, which creates a very narrow band of incredibly hazardous weather, packed with gusty, turbulent winds. A slow-moving cold front, on the other hand, has a shallower leading edge. This results in a much broader area of stable stratus clouds trailing behind the front, but you can still absolutely expect a large number of vertical clouds to form as well.
Section 4. Stationary and occluded fronts.
Look, weather isn't always as simple as one mass perfectly displacing another. Sometimes things just get messy. First up is the stationary front. This is essentially a meteorological stalemate. You have two air masses that are relatively equal in power. Neither has the energy to displace the other, so the frontal boundary just stays stationary. The danger here isn't necessarily violent turbulence. The real danger is that this front can influence local flying conditions for several days, locking in low ceilings and poor weather right over your intended flight path.
Now, let's see how this builds when a fast-moving cold front catches up to a warm one. You get an occluded front. There are two variations here. First, a cold front occlusion happens when the fast-moving cold front is actually cooler than the air ahead of the slow-moving warm front. It replaces the cool air and forces the warm front up, remaining relatively stable. Then you have a warm front occlusion. This occurs when the air ahead of the warm front is actually colder than the advancing cold front. The cold front is literally forced to ride up and over the warm front. This warm front occlusion is notoriously unstable and much more severe, very often hiding embedded thunderstorms.
When it comes to the specific conditions for occluded fronts, you can expect poor visibility and light to heavy precipitation before and during passage, with things gradually improving afterward. Pay special attention to the temperatures here. In a cold occlusion, the temperature drops as the coldest air moves in at the surface. In a warm occlusion, the surface temperature might actually rise slightly or become milder because the advancing air is warmer than the freezing air it's overriding. Both scenarios require extreme caution and a totally solid instrument scan. Section 5. The danger of icing. We are now shifting our focus from macro-level weather systems down to the micro-level, the specific physical threat that visible moisture poses to your aircraft. Icing generally falls into two distinct categories. First is induction icing, which literally starves your engine of air. The most common type here is carburetor icing, occurring right in the venturi. And get this, it can happen even when you think it's warm outside. Specifically, it happens between -7 degrees and 21 degrees Celsius, as long as relative humidity is above 80%. You counter this performance loss by promptly applying carburetor heat. The second category is structural icing. This builds up on any exposed surface of the aircraft, causing a dangerous loss of lift, increasing the aircraft's weight, and creating severe control problems. So, the crucial point is this. For structural icing to occur at all, you absolutely must have two conditions present: visible moisture and temperatures below freezing. When those conditions are met, you might face one of three types of ice. Rime icing happens when tiny water droplets strike the aircraft and freeze instantly, trapping air inside. It looks milky, and it changes the shape of your airfoil's leading edge, which reduces lift, but thankfully it is relatively easy to remove. Clear icing, though, that is the major concern. This happens when large, supercooled droplets, like freezing rain, strike the surface and slowly freeze. It has very little air trapped inside, making it heavy, hard to see, and incredibly hard to remove. A terrifying fact for you: severe, clear icing can alter your aerodynamics so quickly that you can lose control in a matter of minutes. Finally, mixed icing is a dangerous combination where rime and clear ice form simultaneously.
Which brings us to our final point, and a really crucial question for you to ponder. Next time you look at a weather chart during your pre-flight prep, will you just see lines and symbols, or will you see the dynamic, invisible forces shaping your flight? Mastering weather theory isn't just about passing a written exam. It is the absolute key to making smart, authoritative decisions in the cockpit. By understanding how air masses behave, decoding the battles fought at the fronts, and deeply respecting the real danger of icing, you are taking true command of your safety as a pilot. Keep learning, keep analyzing those charts, and always fly safe.